So, math is a very systematic approach to understanding our world. In fact, algebra is a very systematic way of handling a lot of problems. And so, just like one would expect to have a good understanding of how to build a house, what tools are involved, and not just going and starting to build a house without thinking about things beforehand, we want to be familiar with our tools. What is it that we're allowed to do? What are things that are going to work or not work when we work out our algebra problems? So for this reason, we're going to look at some axioms or basic principles or basic concepts that are going to be the fundamental reasons for why we can do or not do certain things in algebra. One of the important properties that we're going to discuss is the distributive property. This is fundamental to a lot of things that are going to be useful to us in algebra in terms of problem solving. All it is basically a multiplication property. It says that if we have a value outside of a given quantity, in this case 3x minus 5, that we're going to distribute it by multiplication to each of the terms inside of our quantity. So 4 gets distributed to the 3x. 4 also gets distributed to this subtract 5. When we multiply it, we end up with 4 times 3x giving us 12x. As well, 4 times minus 5, we're going to pretend like this subtract is a negative, and it will work out the same. We'll see some examples in class as to exactly why that takes place, but 4 times what appears to be a negative 5 is going to give us a negative 20, but we would write subtract 20. We'll look at some examples that justify this distributive property. One of the big mistakes that students often make with the distributive property is forgetting to distribute to someone within the group or quantity. Just like if you were asked to give out tests in a class, the teacher would expect you to give it to everyone. When you distribute to a given quantity, each term has to be multiplied by that factor or value. So as an example, if we have here A times the quantity of B plus C, then A has to be given by multiplication to B. So in other words, A times B becomes AB. And then A also has to be distributed to the C. In other words, A times C becomes AC. Remember that when we're writing variables with multiplication, that we're just putting them together. So when you see items that are just put together with no operation sign in between it, it means that we're multiplying them. So similarly, with this numerical example, 6 gets distributed to the 7 by multiplication. So 6 times 7 is 42. 6 times 8, we also have that distributed as well. 6 times 8 is 48. In this case, we actually have numbers, so we can see that the distributive property makes sense from what we know already about numbers. Because if we were to multiply 6 times 7 and then 6 times 8, we end up with 42 plus 48. If we add 42 and 48, then we end up with 90. So we're bringing all our equal signs down. This side is self-contained. Everything remains the same. In other words, we're working everything on this side independent of what's going on the other side. So we end up with 90 over here. Were we to work this side independently as well, remember from order of operations that we add 7 and 8 first. That gives us 15. 6 times 15 is 90. So we end up with 90 on both sides. In other words, what happened on this side, on our right side of the equation, is equivalent to what happened on the left. So what we know about the distributive property is equivalent to what we would have already known about working with order of operations. That's important to know because we have a numerical example here, but sometimes we don't have numbers inside of our quantity as we had up here at the top. we had variables. So knowing that the distributive property works is very useful in terms of manipulating or handling values within an equation. So here's another example. This time it's subtraction, but remember the distributive property works regardless of whether it's addition or subtraction that we have within our quantity. So in other words, don't forget to distribute to each of the terms within our quantity. So distribute to the b and it becomes AB. Distribute to the C, and remember this subtraction sign, we're going to pretend like it's a negative. So a positive times a negative is a negative, but it actually isn't negative, it's subtraction. So when we decide that our answer is negative, we just put a subtraction sign instead. So A times B, we write that as AB. A positive A times subtract C, we write that as subtract AC. Again, notice that we end up with the same value on the left side if we were to use order of operations as we would if we were to use the distributive property. So 7 minus 8, if I have $7 and someone tries to take 8 from me, then I owe them $1. So it would be negative. 6 times negative 1 is negative 6. So on this side we have negative 6. On the right side, 6 times 7 is 42. 6 times 8 is 48. If I try to take $48 from $42, then I would be left with a debt of $6. So we end up with exactly the same situation. So no matter whether it's addition or subtraction, the distributive property works. To associate basically means to group. So when we're talking about the associative property of addition, it really is just a grouping property. Given the problem 2 plus 3 plus 4, you can choose to either add or group 2 plus 3 first and then add in the 4, or we can group the 3 plus 4 first and then add in the 2. In this case, we have 5 plus 4, which is 9 on the left side. In this case, we have 2 plus 7 on the right, which is 9. So we end up with 9 on this side and 9 on that side. So it doesn't really matter how we group them. We end up with the same answer. If we were to generalize this to variables, given the expression a plus b plus c, we can group a plus b and leave the c by itself, or we can group the b plus c and leave the a by itself and end up with exactly the same expression, or exactly the same, we end up with equivalent expressions. The associative property doesn't just work for addition, it also works for multiplication. So were we to do 5 times 3, that's 15. 15 times 6 is 90. But if we had those same values, 5, 3, and 6, but this time group the 3 and the 6 first, 3 times 6 is 18, and 18 times 5 is 90. So we end up with this value and this value being equivalent. So it doesn't really matter how we group them with multiplication, it's going to be equivalent. So we can associate or group, for example, A and B together and put C as one factor, or we can put B and C together and leave A as a factor. So the associative property is going to be useful in terms of, it's really just like a tool that's going to help us to solve certain other problems later on. The commutative property is a very useful tool. Just like we go back and forth between school and home, home to school, that we can commute the expressions in an addition problem, or the terms in an addition problem. So if we have 5 plus 6, we can turn it around and put the 6 in front and make it 6 plus 5. We get exactly the same answer. So 5 plus 6, we get 11. 6 plus 5, we get 11. Why this is useful is because sometimes you might have an equation that looks like this. Y equals 2x minus 3. Or rather, let's change that. You might have an expression like y equals 7 plus 3x. And it may be convenient to rewrite it with the 3x in front. We know that it's okay to do that because this is addition, and with addition we can interchange the two terms and it's exactly the same. So if I want exactly the same equation, I still have y, I still have an equal sign. If I switch the 3x and the 7, that side is exactly the same because of the commutative property. So now I've just rewritten the equation in a way that makes sense for what I'm trying to do. The commutative property is also applies to multiplication. So notice that we didn't say anything about division though. This only works for multiplication and addition. So for example, if we have 1 times 5, it's the same value as 5 times 1. Similarly, if we do 2 plus 3 times 5, or in other words, this is just 5 times 5, we can change the order and make it 5 times 2 plus 3, and it's exactly the same. So when we have two factors, we can switch them around and it's exactly the same problem. Just to make sure that you get that, let's just multiply this out, or find the value. 2 plus 3 is 5. 5 times 5 is 25. So on the left side, we end up with 25. On the right, 5 times 2 plus 3 is basically the same. It's 5 times 5. So we still end up with 25. So we can switch it around if we want to, but we'll end up with exactly the same. That's what the commutative property says. So why that's useful is, let's say we had this expression, 3x plus 2, that quantity, times 7 written this way. And let's say we got confused about about it being written in this way. Well, we could rewrite it with these values, with the 7 in the place of the 3x plus 2 and the 3x plus 2 in the place of the 7, because that's what the commutative property says. It's okay that we're not changing the problem by switching those around, or we're not changing any values by switching them around. So were we to write it as 7 times the quantity of 3x plus 2, so now we might get it. Now we'll see that we're really just, in both of these examples, we're really just distributing the 7 to the 3x and the 2. We could have seen that here too, 7 times 3x and 7 times 2. But sometimes for some people, it's easier to see it this way. But in any case, 7 times 3x would give us 21x. 7 times 2 would give us 14. So were we to finish this out with a distributive property, we would end up with 21x plus 14. Your identity is who you are. A number's identity is its value. So the identity for addition is going to keep the value the same. For example, if we look at 0 plus 5, this 0 kept the value as 5. If we look at 0 plus 19, this 0 kept the value as 19. Similarly, 0 plus any of these other numbers will retain its value as well. For that reason, 0 is called the additive for addition, the additive identity. For multiplication, we want the value to remain the same as well. And we know the only thing we can multiply by that's going to keep the value the same is 1. So 1 times 5 is 5. 1 times any number is that same number. 1 times any number is that same number, and so on. So the multiplicative or multiplication, so the multiplicative identity is 1. So it doesn't matter whether we put a number or a variable, it will be exactly the same. So 1 times a is a. It's interesting to note that if we were to write 1 times x, it would just be x. 1 times y, it would just be y. So working backwards, what that means too is that if we see y by itself, then it's really 1 times that number. If we see x by itself, it's really 1 times that number. These have the same value. The inverse property of addition just says that if somebody gives you a number, that there's another number you can add with it to get 0, which is the additive inverse. So we know that because if I give you 3 and you add -3, then that's 0. Remember, adding an opposite is the same as subtracting. So 3 plus a -3 is really equivalent to 3 minus 3. So when we see, just to break it down a little bit, adding a negative, it's really just like subtraction. So this is really 3 minus 3. So 289 plus a -289 is really 289 subtract 289, which is 0. So the additive inverse is really just the opposite of that number. So let's say that you were given some numbers. Let's say we said 8. What do you suppose the additive inverse of 8 is? It would have to be -8, because if you add them, you get 0. What about 9? What's the additive inverse of 9? It would have to be -9, because if you add them, you get 0. What if we had -15? What's the additive inverse of that? Well, obviously it's the opposite, so it would have to be 15, because if we add them, we end up with 0. So the additive inverse is, another name for it would just be the opposite. It's what we add to a number to end up with 0. So the inverse, as we discussed before, is going to get us back to the identity. So for multiplication, remember the multiplicative identity is 1. So we want a number that when we multiply it by another number, we get 1. So how's that going to work out? Well, we have to remember what happens when we multiply certain numbers. For example, if we did 18 times 1 over 18, some get stuck on that and aren't really sure why that would have to be 1. Well, if you think about it, 18 is really 18 over 1, or 18 divided by 1. So this value here is the same as this one here. 18 divided by 1 has the same value as 18. So this problem that we have here may be written as 18 over 1 times 1 over 18. And I apologize for using an x for multiplication. That can kind of get confusing, so let's use a dot here. So we could, from what we know about multiplication with fractions, the very long way is to multiply left to right. So 18 times 1 and 1 times 18. If we do that, we end up with 18 divided by 18. And 18 divided by 18 is going to give us 1. So we know that this is true. 18 times 1 over 18 is 1. If we go through the same reasoning with 23, we would also end up with 1. So 23 is the same as 23 over 1. If we multiply that by 1 over 23, we end up with 23 over 23, and 23 divided by 23 is 1. So we know that that's true. So long story short, the multiplicative inverse, there's another name for it. It's the reciprocal. So when we have whole numbers, the reciprocal would just be 1 over that number. So if I give you 7, the reciprocal or multiplicative identity would be 1 over 7. Because if we multiply these, we end up with 1. If I gave you 9, you'd have to multiply by 1 over 9, because you'd end up with 1. So the multiplicative identity of, let's say, something that's a fraction, if you have 3 over 5, the multiplicative identity would be 5 over 3, because that's the reciprocal. If we were to do left to right multiplication, 3 times 5 is 15. 5 times 3 is 15. So this is going to end up being 15 divided by 15, or 1. So in other words, if we multiply a number by its reciprocal, we get 1. So we multiply a number by its reciprocal, we get 1. We multiply a number by its multiplicative identity, we get 1. So these are multiplicative identities of each other, or you can say, multiplicative inverses of each other, or reciprocals of each other. So as long as we're multiplying by the reciprocal, we're going to end up with 1. Because the equal sign means that two amounts have the same value, then it really doesn't matter what side of the equal sign we write them on. We can interchange them and it's exactly the same. This is the symmetric property. So in other words, there's symmetry around the equal sign. So 5 has the same value as 2 plus 3. 2 plus 3 has the same value as 5. So we can switch them around. Why this is important is, let's say you have to solve an equation. Most people have no problem solving this. You would have to subtract 3 from both sides, and then you divide both sides by 2, and so on. But while they wouldn't have a problem solving that, they do have a problem trying to solve this. Let's say you have 9 equals 5x plus 2. Because our values are on the, because our variable is on the right side now, for whatever reason they get confused. But what we've just written here, using the reflexive property, using the symmetric property, we can interchange the 5x plus 2 with the 9 and end up with exactly the same thing. So in other words, this right side, we can interchange it with the value that we have on the left side, and it would be exactly the same. So we can have 5x plus 2 on the left side instead of the right, and we can have our 9 on the right side, and it is still equal. So we could solve either of these equations and end up with the same answer, essentially. The transitive property basically is like a chain of thoughts. So one connects the other to the other. So for example, we know Peter Parker and Spider-Man, likely. So if we say Peter Parker is Spider-Man, and we know Spider-Man is battling Dr. Octopus, then that means Peter Parker is battling Dr. Octopus. So let's go through that one more time. Peter Parker is Spider-Man. Spider-Man is battling Dr. Octopus. So that means Peter Parker is battling Dr. Octopus. So what that means is basically we can connect things that are equal. So if 2 plus 3 is 5, and 5 is the same as 4 plus 1, then that means 2 plus 3 has the same value as 4 plus 1. They're connected by this 5. Same thing here with this 8 minus 1. If 8 minus 1 is 7, which we know is true, and 7 is the same as 2 plus 5, then that means that 2 plus 5 has the same value as 8 minus 1. And that's all this is. 2 plus 5 has the same value as 8 minus 1. So this is important later on. It will be important later on when it comes to solving certain equations or groups of equations known as systems of equations. It may be a useful property as well in other areas, but that's one of the primary uses in what we're going to be doing this year. The reflexive property doesn't really need a whole lot of explanation. A number equals itself, period. 2 plus 2 is 2 plus 2. 5 plus 4 is 5 plus 4, and so on. The multiplication property of 0 is really important. It's going to come up later on when we're trying to solve quadratic equations. All it says is that if we have 0 as an answer to a multiplication problem, that at least one of the numbers, if not both of them, were 0. And that works out basically because 0 times any number is 0. So if we get 0 as a product, one of the factors has to be 0.